Okay, in today's lesson we are going to be looking at our irrational numbers that are called radicals, right? So a radical is like a root. A root 5 is irrational, and we're going to talk about how can we simplify some of these irrational numbers, which we call radicals, right? So that whole thing is called a radical, okay? The number underneath is called the radicand, and this is the index that's tucked in the pocket. So that is the square root of 2. We don't write 2 because that's the lowest possible index you can have. Right? So this would be the square root of 9. Okay, and what does the square root mean? Square root means find two possible numbers that are identical to give it, and write only one of them. So if a number can be written as two identical factors, then the square root of the number is that factor, right? So the number one mistake I always get is I always get people writing the square root of 9 is the square root of 3. Once you've taken the square root, think of the square root as like a verb in English. It's a function. It's doing something to this number. So once you've done something to the 9 and you've taken the square root of it, you don't write that anymore because you've done it. It's kind of like your division sign, right? If I take 9 divided, well, let's start with a better number. If I take something like 10 divided by 2, when I do the operation to 10, I just write the answer to it. Okay? So once you take the square root of a number, you don't write the root sign anymore. Okay? Now, some numbers you can't take the square root of because they're not perfect squares, right? So square root of 5 is not a perfect square, so you can't take the square root of it. And so you leave it as a square root of 5 because we know that if the write out the decimal of it, it goes on forever because irrational numbers their decimal representation never terminates or has a repeating pattern. So the easiest way to write root 5 in its exact form is write root 5. So we have to be able to work with radicals. Okay. Same thing with cubed root. For example, the cubed root of 8. Well, the cubed root, when it's a cubed root, you must write that little 3 inside the pocket of the root sign because that's the index, okay? It tells you you want to find 3 numbers when multiplied together give you 8, and those 3 numbers must be identical. They must all be identical, right? So if they're all identical, then when you take the cubed root of 8, you just write one of the 3, and then that becomes the answer. The cubed root of 8 is one of those 3 identical factors. Don't write the cubed root sign anymore, right? But if I gave you the cubed root of 10, well, there are no 3 numbers that multiply to give the cubed root of 10, so I just leave it in its exact form like that, okay? But if you can take the cubed root of it, then you would, right? Again, if you take the cubed root of negative 8, you can make 3 numbers that multiply to give negative 2, right? And so 3 negative 2's give you negative 8. Oh, so the cubed root of negative 8 is negative 2. But if I gave you something like the square root of negative 25, can you make 2 identical numbers to give negative 25? Well, 5 times 5 is 25, so no. But if I make them both negative, that's still a positive. So it's impossible to take the square root of a negative, but you can take the square root, the cubed root of a negative, right? So we have to think about that as we go along here as well. So when we see roots, we could just type into our calculator, right? The square root of 300 and get a decimal, 17.3205, etc. But root 300 is its exact form, so I'm going to leave it like that. But we can also talk about how can we simplify root 300 down to its simplest form. Just like fractions can be reduced down to a number that's equivalent to it, right? So if we divide by 2 divided by 2, radicals can be simplified as well down to its simplest form. And how do we simplify a radical? Well, we find numbers that we can take the square root of. And we take the square root of those. So we have to find a factor, a number that divides into 300 that's a perfect square. So let's think about all those numbers we can take square roots of. Well, we can take the square root of 1, but it's 1, so it doesn't really matter. It doesn't get us anywhere. So I'm going to ignore 1. But we can take the square root of 4. We can take the square root of 9, right? 2 by 2, 3 by 3, 4 by 4, 5 by 5, 6 by 6, etc. Whoops, that's supposed to be 49. 8 by 8, 9 by 9, 10 by 10, and I can keep going on forever, right? Those are perfect squares. Those are the numbers I can take a square root of. So I look through this list. Which one of these divides into 300? Oh, look, 100 does, right? So it can become root 100 multiplied by 3. And when you have a square root, you can break it into root 100 multiplied by the square root of 3. And the square root of 100 is 10, right? Because 10 times 10 is 100. All of these are perfect squares. The square root of 36 is 6. The square root of 49 is 7. The square root of 64 is 8, etc. Okay? But we can't take the square root of 3, so it's multiplied by root 3. Well, in math, we don't go 10 times root 3. We don't write that multiplication sign. We just squish it together. So that I would read that 10 root 3, which means 10 times root 3. All right? So this is the simplified version of root 300. Okay? So if I gave you something like root 50, then it would be 25, because 25 goes into 50 twice. Right? I don't care it's 5 times 10, because 5 is not a perfect square, 10 is not a perfect square. I can't take the square root of either of those. But I can take the square root of 25, and I write that first. And then I take the square root of it, so I don't write it under a root sign, so the square root of 25 becomes 5. But the 2, I cannot take the square root of it, so it stays inside. And so that is simplified. A lot of times, this is what I get when I give root 72. So if you want to pause it and try this yourself, it's a good idea on videos to pause and try things and then watch my solution. Because you learn from your mistakes, or you say, yeah, I got this, move on, right? So if you pause and try this, and then come back, you'll see if you've made the typical mistake that I typically see. Most people find a perfect square that goes into 72, and they would pick something like 9, right? And they would say, oh, look, well, the square root of 9 is 3, and it's 3 root 8, and then they'd move on to the next question. But look at 8. What do you notice about 8? Is there still a perfect square that goes into 8? Look at that list. Oh yeah, 4 goes into 8. So sometimes you don't always choose the largest perfect square. So it's not the end of the world. You can just keep going, and you can now simplify this. Or you could start again and look for a larger one. Let's continue on. So if I have 3 root 8, I know that 8 becomes 4 times 2, right? And so what I do a lot of times is now when I write this, since it's 3, I write 3 bracket, and I take the square root of 4, which is 2, and the 2 stays inside, and now I can multiply the 2 and 3 together and get 6 root 2. Okay? If you had found the perfect largest square first, it just saves you time. If you'd noticed 36 times 2 is 72, and the root of 36 is 6, you could have gotten there a lot quicker. So tip is always look for the biggest perfect square if you can find it, but if you didn't, always check that your radicand doesn't still have a perfect square that goes into it, just to be safe, that maybe perhaps you missed one. All right, let's try a cubed root one. So we need to look at our perfect cubes. So our perfect cubes, again, 1 we're going to ignore because 1 doesn't simplify it. It's like a fraction. If you multiply the top and bottom by 1, it's the same thing, so it doesn't change it and simplify. So we're going to look at our perfect cubes. So 2 times 2 times 2 is 8. That's our smallest positive perfect cube. And then we're going to go with 3 by 3 by 3, 4 by 4 by 4, 5 by 5 by 5, right? Or 2 cubed, 3 cubed, 4 cubed, 5 cubed, 6 cubed, right? And so on. They grow so quickly, there's not so many of them, right? So it's easier with cubes because there's less numbers to check. So which one of those? Oh, I can see 8 goes into 40. And again, whenever you have a perfect or a cubed root, you have to write that index every time. Even if it's sloppy, I don't care. Stick it in there, right? And make sure it's small. I'd rather have it small and sloppy than big, because a big 3 means 3 times root 8, whereas a little index means it's the cubed root of. So make sure you don't confuse 3 times square root versus the cubed root. So I'm going to get 8 times 5, and I know the cubed root of 8 is 2, and then I write cubed root of 5 there. Okay? And that's simplified. All right. We're going to talk about powers now. So I'm going to just take a side note over here and talk a little bit about powers. Okay, so numbers, we know when numbers are perfect squares, right? We know that 9's a perfect square because it's 3 by 3. We know 100's a perfect square because it's 10 by 10. But what happens when we write our number in power form? Okay, so we write something like x to the power of 2. Is that a perfect square? Can that be written into 2 identical factors? Yes, it can. Therefore, the square root of x squared is x, right? Can x3 be written into 2 identical factors? No, it's impossible. So x cubed is not a perfect square. X to the 4, though, can be written as x squared by x squared, right? So therefore, then we can say, well, the square root of x to the power of 4 is x squared, right? One of those 2 identical. So using that logic, we can say that any even exponent, right, when it's a power, if the exponent is even, we can break it into 2 identical powers multiplied together, right? By breaking that power in half, right, because we know when we're multiplying powers, we add the exponents if the bases are the same. Therefore, the square root of any even power is half the power. Okay? So m to the power of 10 I can see as a perfect as square, right? Whereas y to the power of 5 is not a perfect square. Well, let's take a look at cubed roots. Okay, let's take a look at cubed roots. So if I say x to the power of 3 can be written as 3 identical factors, therefore the cubed root of x cubed is just simply x, right? Well, x to the power of 4 can't be written as 3 identical, x to the power of 5 can't be written as 3 identical, but x to the power of 6 then, because it can be x squared times x squared times x squared, right? 2 plus 2 plus 2 is 6. When we're multiplying, we have the same base, we add the exponents. So these are powers. So this is a perfect cube, this is a perfect cube, right? 6 is not a perfect cube, but the power is a perfect cube. Be careful with that. It's not the exponent that's a perfect cube, it's the power. What it would equal if we knew x, right? And then further down, the next possibility would be 9 because it's x cubed times x cubed times x cubed, right? So we're starting to see that if it's a multiple of 3, then it is a perfect cube. And you can take the cubed root of any multiple of 3. So for example, the cubed root of x to the power of 12 would be x to the power of 4, because 3 4s make 12. That's in power form. So what do we think when we go over to this question when it's a power of 4, when it's a 4th root, right? Well, x to the power of 4, the 4th root of x to the power of 4 is x, because 1 of 4 identical. The next possibility would be the 4th root of x to the power of 8 is x squared, right? And the 4th root of x to the power of 12 would be x cubed, right? So I can see x to the power of 8 is a perfect 4th power, and that would be x squared would be the part that's left over. Okay, same thing with y. That would become y to the power of 4. That's the largest 4th power that goes in it. It would have to be 4, 8, 12, etc., right? And y to the power of 1 is left over. So this is my perfect 4th power, and so is this. So those are the ones that are going to be coming outside of my root, because I can take the 4th root of them. So the 4th root of x to the 8th becomes x squared, right? 4th root of x to the 8th becomes x squared, That one's been done. The fourth root of y to the power of 4 is just y. That one's done. Okay. X squared can't be done, so it stays inside. And y to the power of 1 stays inside, right? And I have my little, gets messy here, but I have my little index tucked in the pocket there. So these ones are kind of tricky, so let's try another one again if you want to pause the video and try this on your own. And then you can come back and see how you did. All right, here we go. So, powers of 3, right, would be a power to the power of 3, to the power of 6, to the power of 9, to the power of 12. Multiples of 3 are perfect cubes. So the largest multiple of 3 would be x to the power of 6. And then I break it up, right? 6 and 2 is 8. The largest multiple of 3 going into 10 would be y to the power of 9 times y. And z to the power of 2, nothing. There's nothing I can do with that because 2 is smaller than 3. So the only ones that are perfect cubes are x to the 6th, y to the 9th. So I'm going to take the cubed root of x to the 6th, break it into 3 identical, so that becomes 2. I'm going to take y to the 9, and that becomes y cubed. And then everything else stays inside. So x squared I can't take the cubed root of, the y I can't take the cubed root of, and the z squared I can't take the cubed root of, right? So when they're powers, that's what you do. But if it was a number in front, like if I threw an 8 in front, well, the 8 is not a power. I can only take the cubed root of it if it's a perfect cube. Oh yeah, then I could take the cubed root of 8, which is 2. So remember, numbers versus powers. Okay, try one more. See how you do. So 54, like I was just saying, is a number. So I have to find an actual perfect cube that divides into 54. And I see 54 as 27 multiplied by 2. 27 being my perfect cube. Y cubed is also a perfect cube. I don't have to do anything with it. I don't have to break it down. It is a perfect cube. So I'm going to take the cubed root of 27, which is 3, the cubed root of y cubed, which is y, and the 2 stays inside. All right? So it's 3y times the cubed root of 2. Okay, you can pause the video, try these out, and then I'm just going to go through these quickly. All right, this is going to become 2 times, and 75 is broken into 25 by 3. So it's going to become 2 times 5 root 3, which becomes 10 root 3. All right, those are both outside, so we're now able to multiply. Here, I'm just going to ignore this number out front and just complete the inside. 3 over 10 multiplied by the cubed root of, and I need to find the biggest cube that goes into 250, and I'm going to say that it is 125 multiplied by 2, because the cubed root of 125 is 5. So I'm going to get 3 over 10 multiplied by 5 times the cubed root of 2, or 5 over 1 times the cubed root of 2. I'm going to see that these 5's cancel, and now I'm going to get negative 3 times the cubed root of 2, and that's the answer. Here, 16 is a perfect fourth root. If I don't know what my perfect fourth powers are, then I can generate them. 2 to the power of 4 is 16, right? 3 to the power of 4 is 81. 4 to the power of 4, etc. You can they grow really fast, so there's not a lot to choose from. So the fourth root of 16 is 2. The negative is like a negative 1 outside. It just comes along. It's negative, right? Whereas if I put the negative inside, well, then I need those 4 numbers to multiply to give the negative, right? This negative is not part of the root. It's the coefficient type of the, right, the number in front that's being multiplied by negative 1. Whereas the negatives inside, I actually have to take the fourth root of negative 16. Can I have 4 numbers that multiply to give a negative? Well, no. 4 negatives is positive and 4 positives is positive. I can't have 4 identical numbers giving me a negative, so this is not a real number. Sometimes we could ask you to go the other direction. Could you convert to an entire radical? So if it's a mixed radical, can you go backwards? So instead of taking the 8 out of the root by taking the square root, we're going to put the 8 back in. So the opposite of square rooting is squaring. So you're simply putting it back in by squaring it, because 64, the square root of 64 is 8. So when you put it back in, it becomes 64. And then you can just type 64 times 3 and get this is the square root of 192. Same thing with powers. When I put it back in, it's going to become x cubed all squared multiplied by b all squared, and the c is already there, so you just let it be. And so now I'm going to get a to the power of 6 times b squared times c, and then I'm just not going to write those multiplication signs, and I'm going to write it like that. All right, and again, pause whenever you like, try, and then check your answers. So here I'm going to put the 4 inside and get 16. I can, oops, sorry, I missed my little cube in there, right? So I'm not going to get 16 because this is a cubed root function. So when I put the 4 inside, I get 64. When I put the x inside, I'm going to get x cubed. I have my 2x already inside there, so now I can multiply that together. And I've been missing writing my little cubed root, so I got to make sure that index is there when it's not a square root, so that it makes sure that the function is written properly. So 64 times 2 is 128. X cubed times x is x to the power of 4. All right, you guys try these ones. Excuse me. And then I will put these answers up, and you can see how you've done. All right, this is going to become 16 by 3, which gives you 48. This is going to become negative 5 cubed. When it goes inside, multiplied by 12. Well, negative 5 cubed is negative 125 by 12, which gives you, oops, I'm missing my little index again. It's going to give you negative 1500. Okay, this one's going to give us 2x squared, which gives us 4x squared, all over 3y. When you put it in, is going to be 9y squared. And the 3y is already in there. Right? Since that's a fraction, I'm going to write that as a fraction to be able to multiply. And I'm going to get 12 divided by 9, or we could cancel right away. We can say, well, this just becomes 3, right? And then even a y cancels there. So we're going to get 4x squared all over y. And we'll try this last one over here. Again, when I put them on the inside of this cube root, this is going to be 1 over 8x cubed it, multiplied by the 5x that's already in there, which I made into a fraction. And now I can see the x cancel, so one of the x's cancel off the bottom. And so now I'm going to get the cubed root of 1 times 5 is 5, all over 8x squared. All right, so you're putting them in. If it's a fraction, you just have to be able to multiply your fractions, or you could have just gone numerators, multiplied, and then simplified. Either way. One last little piece is we need to remember about restrictions on our variables if we have numbers or variables inside your radical, or we call that the radicand. Okay, so if we have 5 times a, right? For example, if a, well, let's take a look at this. Remember, can we take the square root of 0? Yeah, it's 0, right? But we cannot take the square root of a negative. That is not a real number, right? But anything 0 and above is okay. But we cannot take the square root of a negative. So what kind of values for a would make this negative? right? So when is 5a greater than or equal to 0? Well, it's true when a is greater than or equal to 0. So the restrictions on my variable under the Radican means the a has to be greater than or equal to 0. Because if a is less than 0, I'm getting a negative, and that will give me a not a real number. Okay? So I just take a look at the whole number underneath, and we can even do it algebraically. You can guess and check this one easily. Well, 5 gives me 0, right? So if it's greater than or equal to 5, right? But sometimes it gets a little bit more complicated, right? You can just do it algebraically. If it gets more complicated and you move the negative 5 to the other side, it becomes positive 5, right? So x has to be greater than or equal to 5. Whereas if I gave you one where it was like 5 minus x, right? Well, when you solve that, and you move the 5 to the other side, you get negative x is greater or equal to negative 5. Well, it's kind of like the opposite of x is greater or equal to negative 5. So whenever you divide both sides by a negative in an inequality, your inequality sign reverses. So x is actually smaller than or equal to 5 here to make that true. So you have to be a little bit careful with that when you're just guessing and checking. Here, x plus 7 has to be greater than or equal to 0, or x has to be greater than or equal to negative 7. Okay? And again, pause and try if you like. 3a minus 7 is greater than or equal to 0, so we solve this. 3a is greater than or equal to 7. Divide both sides by 3. A is greater than or equal to 7 over 3, or we can write that as 2 1/3. Okay? And last but not least, negative 2a is greater than or equal to, sorry, I wrote that wrong. Negative 2a plus 1 is greater or equal to 0, so the whole radicand has to be bigger than 0. Whatever this expression is, greater than or equal to 0. Now we solve for the variable that makes this statement true. Negative 2a is greater than or equal to negative 1. Divide both sides by negative 2. Oops, I'm dividing by a negative, so my sign reverses. The opposite is true, right? Because why is that true? Because I know that 3 is greater than 2. But if I multiply both sides by negative 2, the opposite is true. Negative 6 is no longer greater than negative 4. It's now smaller than, right? So whenever you multiply or divide by a negative, your inequality has to reverse. Couple special cases. When you have an even power, and so let's write this. When is a squared greater than or equal to 0? Well, it doesn't matter what a is. If you had negative 3 and you're squaring it, it would be greater than or equal to 0 because 2 negatives makes a positive. So if this is an even exponent on your variable, there is no restrictions. So no restrictions is what I would write. There are no restrictions. A is in the set of all real numbers. Okay? Same thing with cubed rooting. Right? Are we allowed to take the cubed root of a negative? Yes. 3 negatives multiplies to give a negative. Same thing with a fifth power. 5 negatives makes a negative. Or a seventh, sorry, not power, but root. A seventh root. 7 negatives makes a negative. So if this root is odd, then there are no restrictions. So you need to know when to write no restrictions. Okay? And you need to go, well, when can that be a negative? When is it okay for that to be a negative? It's okay for that to be a negative when you're squaring a negative or fourth root powering a negative because it'll become positive. Or when you're taking an odd root of underneath, then it doesn't matter if it's negative. Okay? So in general, odd index numbers have no restrictions. Okay?